Hello everyone and welcome to the second video of solving some elementary number theory problems from Sierpinski's 250 elementary number problems book. So let's start from where we left. Question number 5. Prove that 2 to the power of 6k plus 2 all that plus 3 is divisible by 19 for all non-negative integer k. From Fermat's Little theorem, we remember that 2 to the power of 18 is always equal to 1 mod 19, given that 19 and 2 are coprime, and 18 is equal to 90 minus 1. So we can get that the cycle of powers of 2 mod 19 is determined by the cycle of their exponents by 18. We can then calculate the cycle of those exponents, which is 2 to the power of 6k plus 2 mod 18. That's 4 to the 64 to the power of k. Reducing that to mod 18 would be 4 times 10 to the power of k. That's 2 to the power of k plus 2 times 5 to the k. Now, calculating all the possibilities that would, which are written in the first line here, we get that for all non-negative integer k, we have to the power of k plus 2 times 5 to the k mod 18 is equal to 4. So 2 to the power of that equation plus 3 is always equal to the power of 4 plus 3 mod 19, and that's 16 plus 3 equal 19. So it's always divisible by 19. The proof is complete. Question number 6. Prove that the theorem due to critique that 2 to the power of 70 plus 3 to the power of 70 is divisible by 13. You can calculate this by hand, but I really don't suggest that. Okay, so 2 to the power of 70 plus 3 to the power of 70 is equal to 128, which is 2 to the power of 7, to the power of 10 plus 3 times 3 to the power of 69. That's equal to 11 to the power of 10 plus 3 times 27 to the power of 13 mod 13. Next, we have 11 to the power of 2 is 121, which is equal to 4 mod 13. That's 4 to the power of 5. And for the next part, we have 27 is equal to 1 mod 13. So 3 to the power of 10, 3 times 27 to any power would be just 3. Then we have 4 to the power of 5 is equal to 4 times 64 to the power of 2. That's 3 to the power of 2 mod 13. 16 to the power of 2, sorry. Which is equal to 3 to the power of 2. That's 4 times 9, which is 36. Mod 13, that's 10. 10 plus 3 is equal to 13, which is divisible by 13. Proof is complete. Prove that 11 times 31 times 61 divides to the 20 to the power of 15 minus 1. Here we can prove that for all individual prime factors of the number, so 11, 31, and 61, and without even calculating the number itself, we can get the answer. For the 11 part, we have 20 to the power of 15 minus 1 is equal to 8,000 to the power of 5 minus 1. Mod 11, that's 3 to the power of 5 minus 1, which is 243 minus 1, 242, and that's divisible by 11. As a fun fact, you can get that if hundreds and two ones of a 3-digit number can add together to give you the number in tens, that number is divisible by 11. So here 2 plus 2 is 4. So the number is divisible by 11. Okay, for 31, we have 20 to the power of 15 minus 1 is equal to 20 times 400 to the power of 7 minus 1. Mod 31, that's 20 to the power of 28 to the power of 7 minus 1. rewriting as prime factors, we get 22 to the power of 16, 5 to the power of 1, 7 to the power of 7, minus 1. And we can multiply 7 and 5 to get 35. That's 4 mod 31 to get 22 to the power of 18, 7 to the power of 6 minus 1. That's 56 to the power of 6 minus 1. Mod 31 is 25 to the power of 6 minus 1. That's 625 to the power of 3. Again, getting it to the mod 31 is 5 to the power of 3 minus 1. And that would give us 124, which is 31 to the 31 times 4. That part is complete as well. So for the 61 part, we can get 8000 to the power of 5 minus 1, which is 9 to the power of 5 mod 61 minus 1. That's 81 to the power of 2 times 9 minus 1. Reducing that to the mod 61, we get 20 to the power of 2 times 9 minus 1. That's 400 mod 61, which is 34 times 9 minus 1. That's 5 times 61. So the last part is done as well. For question number 8, we have prove that for a bigger than 1 and positive integer m, we have GCD of a to the power of m minus 1 over a minus 1, and a minus 1 is equal GCD of m and a minus 1. So this proof involves binomial theorem, which we discussed about in Fermat's little theorem video. We get that the fraction in the left part of GCD is equal a minus 1 to the power of m minus 1 plus sum of k equal 1 to m minus 1, m choose k, minus 1 to the power of k, a to the power of k, over a minus 1. And GCD of that with a minus 1, to get the GCD with a minus 1, we can remove the a minus 1 to the power of m minus 1 part, because that's obviously divisible. And given that a over a minus 1 will never be a whole number, that is, a and a minus 1 are always coprime no matter what exponent a has, we get that all the terms in that part are divisible by m, and other than being divisible by m, they are not divisible by a minus 1. So they don't interfere with our GCD, and we can rewrite that whole expression as m in the GCD to get the GCD of m and a minus 1 is equal the GCD we had in the beginning. That's exactly what question asked us to do. Therefore, the proof is complete. Thanks for watching.